This presentation is about decision trees. Decision trees are a useful tool for analyzing many different kinds of decisions, and capacity expansion decisions are one of those kinds of decisions. It's easiest to explain this using an example. So here's an example of a facility expansion problem that we might approach with a decision tree. We've got a company that's considering expanding their facilities, and they've got a couple of different options to allow them to do so. One option is to build new space. Another option is to convert some existing space. Building will give them more capacity, but it's also going to cost more. We're interested in expanding the facility because we're interested in being able to better meet future demand. However, this problem is interesting because we don't know for certain what future demand is going to be. However, it's possible for us to make some estimates about what we think future demand is going to be, and we can see here that there is about a 20% chance of future demand being low, a 70% chance of future demand being medium, and about a 10% chance of future demand being high. The other important input to our decision tree is a payoff table or a payoff matrix, and that's what we've got here in the top half of this slide. We can see our two different options, build and convert, here on the left-hand column, and up in the top row we can see the three different possible states of nature that we just talked about: low demand, medium demand, and high demand. Now, intuitively, looking at the top row, it should make sense that if we build, which is the higher capacity option, and demand turns out to be high, we're going to be in pretty good shape. We've done a good job matching supply with demand. On the other hand, if we build and future demands turns out to be low, we might wind up being stuck with some excess capacity, and we may wind up losing some money, and we can see that's indicated here in this table. You can also see the payoffs associated with converting if future demand turns out to be low and future demand turns out to be medium. Here with converting, for example, if demand turns out to be low, we're still going to lose some money because we added some capacity, but we're not going to lose as much money as we would have lost if we had built. We don't have anything in this box for what happens if demand turns out to be high in a situation where we converted existing capacity, because if that happens, we're going to have to make another decision. And this is really where a decision tree comes into play. The problem is much simpler if we don't have if we only have one decision. The problem is much simpler, and we really don't need a decision tree. But if we've got decisions that are dependent on one another, this is where a decision tree is really a nice tool. So this is kind of a problematic situation here. If we convert, remember that gives us relatively low capacity relative to building. If we convert and demand turns out to be high, that's not a great situation. And if that happens at the end of year 2, because it's not a great situation, we're going to have to make another decision. And that's to lease some additional capacity or do nothing. And you can see that the payoffs, the net present values, coming back to today from those two options are negative $5 million and negative $6 million. So if we converted and live with that for 2 years, and then we leased for years 3, 4, and 5 in a situation where demand is high, the net present value of that is negative $5 million. Again, if we convert the facility and demand turns out to be high, and we live with that for the first couple of years, and then we do nothing, we basically stick with that for years 3, 4, and 5. Well, the net present value there is negative $6 million, so it's not quite as good. So the question becomes, what's the best thing to do? We've got to make this decision right now. Are we going to build or are we going to convert? A good way to analyze the problem is with the decision tree. So let's talk a little bit about decision trees in general, and then we'll show how to solve this problem with the decision tree. When we make a decision tree, we make the tree from left to right. We construct it from left to right. And the tree is constructed basically of nodes and branches. Nodes can be either circles or squares, and they mean two different things. A square is a decision that we make. It's called a decision node. It's a decision that we control, so it's basically an opportunity for us to pick an alternative, or a situation where we have to pick an alternative, such as roll our product out nationally or roll our product out to only one region. Go pro, stay in college. It would be another decision that would be expressed as a decision node. We have to pick one or more options. Could be 3 options, could be more options. As the problem suggested, we've also got situations where we don't know what's going to happen in the future, where a future state of nation is subject to chance. And we indicate those with circles. Circles are called chance nodes, and these indicate circumstances that we don't control. For example, the market expands, the market collapses, I get injured, I don't get injured. We don't know whether those are going to happen in the future or not. Those are subject to probabilities, and we indicate the probabilities on the branches that are associated with the nodes. This will make a lot more sense if we begin to look at an example. So let's develop an example for our problem. So here's the beginning of our decision tree. Here we've got a decision node. Remember, that's a rectangle, and the first decision that we have to make, as it said in the problem, is to either build a new facility or convert existing space. So we've got those two choices, one on each branch. Whether or not those turn out to be really, really great or not so great depends on demand in years 1 through 5, and that is subject to chance, so we indicate that with chance nodes. So here I've created a chance node, and I've created a different branch for each possible state of nature, and on each one of those branches, in addition to labeling it, I've put the probability, and again that's an estimate that I've developed, it's in my problem, for each one of those states of nature on each branch coming out of the chance node. We've got the same situation, the same possible states of nature and the same probabilities if we convert. So we basically just duplicate that here for convert. And the next thing that I've done is at the end of each one of these branches where I can, I've taken my payoff estimates. Remember, those are the net present values that we would expect for our cost and revenue stream for each one of these different, for each option under each demand situation. I don't have anything down here for high demand in the convert situation because remember, I have to make another decision. So I'm going to indicate that with another square, another decision node, and those two decisions, which I'm going to make at the end of year 2, are to either lease or stay, do nothing. If I lease, the net present value of the total cash flows over all 5 years is negative $5 million. If I do nothing, it's negative $6 million. So that's my decision tree. I've built my decision tree. Now that I've built my decision tree, I need to evaluate my decision tree. Evaluating my decision tree is going to tell me what my best alternative is, the alternative that's most likely to give me the biggest payoff. We built the tree from left to right. When we evaluate the tree from right to left. We'll start over on the right side. We move over to the left side. And basically what we want to do, a good way to think about it, is we want to put a number above each node, a dollar figure above each node, and that dollar figure is the expected value of the conditions to the right of the node. Recall that expected value is just a probability times an outcome. So if I go pro, maybe there's a 70% chance that I make $1 million and a 30% chance that I get hurt and I don't make anything. The expected value would be the sum of each probability times the outcome. So 70% of $1 million plus 30% times 0 would be the expected value there. So for each circle, we add together the expected values of the branches to the right, and for each square, we just pick the branch with the highest value to the right. let's evaluate the decision tree that we've created for our facility expansion problem. Remember that we evaluate the tree from the right to the left, which means that we need to start with the decision that we would need to make at the end of year 2 if we convert and demand turns out to be high. And that's indicated over here. Remember, if that's the situation, we're faced with the decision at the end of year 2 to either lease or do nothing. If we lease, we lose $5 million. If we do nothing, we lose $6 million. Because this is a decision node or a square, we simply pick the option that's most attractive. And of course, losing $5 million is more attractive than losing $6 million, so that would be the option that we would go with. So we do two things here. The first thing that we do is we just draw a couple of lines through the branch that we're not interested in, the do nothing branch, the less attractive option. And then we take the expected value of the option that we are going to go with and we put it over the decision node. You can see I've done that here by putting negative 0.5 over the decision node. So now we move left to the next set of nodes, and these are the two chance nodes here to the left of the decision node. Let's start by evaluating the top chance node, and that's the situation here. And recall that when we're evaluating a chance node, we want to determine the expected value. So I've done that here. Recall that the expected value is just the probability times a payoff, or the sum of the probabilities times the payoff. So for example, there's a 20% chance that demand's going to be low, and the payoff there would be losing $3 million. You can see that's reflected here. And the other two probabilities times the payoffs are also reflected here. If you sum those three up, you can see that that works out to 0.8 million, an expected value of 0.8 million. If we evaluate the node on the bottom, do the same thing. Again, it's just probabilities times payoffs, three of them. And if you do the math on that, you'll see that that works out to a payoff of 0.7 million. So I take each one of those payoffs and I put them above the respective nodes. And now I evaluate the next node to the left. That's my final node to the left here. That's a decision node, and of course with the decision node I simply pick the branch with the higher payoff. So here I've got to compare these two branches. The build branch has an expected value of 0.8, the convert branch an expected value of 0.7, and of course I prefer the build branch. I'm just simply going to indicate that by putting two lines through the convert branch, and in this case building is my best option. Given these probabilities that we started with and the payoffs that we started with, the best decision in this case is to build.